All right. Well, welcome to the Abbott webinar series. Today, my name's Steve Feldbauer. I'll be presenting a talk on high volume metal additive manufacturing by continuous debind and sintering. What I'd like you all to share in is that also today, if you follow us, if you're a new or are not following us on LinkedIn, we'd like you to become a new follower of Abbott by scanning the QR code. And then among the new followers, we're going to be giving away a hat and some sweatshirt and things. So please follow us on LinkedIn, and that way you can be kept up to date on future webinars as well as other activities and releases and information that we are sharing. So what I'd like to do is start off and talk about continuous as it relates to the additive manufacturing of metals. And, so many times that when you mention continuous in the additive realm for metal, a binder jet in particular, we hear, we don't produce enough to need a continuous furnace. And it's because they're thinking of the type of furnace that you see here. It's, the traditional pusher style furnace that has a lot of brick and molybdenum heating elements throughout. And it's very expensive. And, sometimes around $1.5 million or above, right? The key is this is the wrong design. Okay. This type of a furnace is not designed for this market. It's designed for a totally different market and a different process. And so what I'd like to talk with you today, talk about today is, where does continuous fit in? And really, what is high volume? Okay. And that's really the key. Do we say, well, how do we define it? Do we define high volume as, it's 1,000 parts a year, it's 50,000, or is it 1,000,000 parts per year, right? And a lot of that relates back to the markets that we service in the additive world, right? That furnace that you saw previously, that's designed primarily for the automotive market, and they're taking orders for one piece in the millions oftentimes. Well, that's not the market we service, right? Our markets primarily are in the defense or the medical industry. And we hope and we target the automotive industry for the future, but as of today, right now, the defense and medical industries are our primary markets and our focuses. And that means our definition of high volume changes, right? And so, also the product size and the dimensions of these different markets influence what is high volume. A larger part is going to require more furnace footprint, right? In terms of processing area, where, in the medical industry, if you're doing, dental components, they're taking a very small footprint as compared to a gear that would be conventionally processed in one of those very large furnaces. So the design of a traditional high temperature pusher is not the right application for the or the right piece of equipment for this application in the additive market.
Steve,
So
why don't you take a poll, see what our attendees, what they consider high volume production per day?
I think that's perfect. Yeah, could you be so kind as to participate? And this will help us get a feel for where you all, what you view as additive manufacturers, what do you consider to be a high volume facility?
All right, so we have 6. And does anyone else want to cast their vote? Okay, so it looks most of you, about half, voted 50,000 parts per day.
Okay, or per year. Okay, so high volume is 50,000. Okay, and you know, oftentimes you'll see that 50,000 is where people are starting into the market, but they're also coupled with a MIM operation. And so when you're looking at the MIM and the additive, it's not uncommon for you to be well over 500,000 parts, but the additive portion, as you had mentioned, is well over 50,000, right? So let's look at let's compare two types of systems and look at the costs and look at where does continuous fit compared to a batch vacuum. And so in that 50,000 part range and above, it's not uncommon for people to be looking at a 4.5 cubic foot vacuum furnace. And these vacuum furnaces have about 2.75 cubic meters of load space per cycle. And if we assume a 2 millimeter by 2 millimeter footprint part that's about a millimeter high, 2 centimeter by 2 centimeter and 1 centimeter high, which is a fairly common size part for the additive world, that means we can put about 800,000 parts through that furnace in a year. And that furnace would cost about $900,000. Now, a continuous debind and sintering furnace that is designed for additive manufacturing would come in right around $800,000. So it's slightly lower capital cost. And this type of a furnace uses an 8-inch by 6-inch boat. Okay. And it would have a capacity of about just slightly over 1 million parts per year. So they're comparable in size. Okay. You can get the continuous furnace is a little less in capital costs, get you a little more, roughly, 25% more capacity. But, that kind of gives us a starting point for our comparison. And so if we look at this, what we're really comparing to that 4.5 cubic foot vacuum furnace is a pusher furnace that is designed specifically for the additive market. Now, you can also do metal injection molded parts in this, but in particular, it's designed for the additive world as well. And so what's different about this is we don't use this brick and moly construction that's very expensive throughout. You'll notice that in the front portion, if we're going from left to right in our view, you notice you would enter in that section that's a little bit shorter in height. That's our debind area. And in that area, because we're not going as high in temperature, right? Most people are going to be well under 650 degrees C. What that means is we can put a lower temperature insulation package, as well as we can use wire wound elements. Okay, so we can reap the benefits of that lower cost construction in that area to lower the overall capital costs. We're no longer looking at the conventional pusher furnace that's all brick and moly elements. We only put the brick and the moly into the area, as you can see, next after the debind area. There's a small area that is designed to take us up to that 1550 temperature for doing things such as the 316 or the 17.4. And then we exit out into a cooling area, and then the boats would then travel out the furnace to the far right and be unloaded, and the boat then cycled back up to the front again. So where do we stand with this type of technology in its cost? So if we look at the cost per part as a function of the production, We're well under $3 per part. As you notice, if we fill this thing to roughly half its capacity, we drop below 25% or 25 cents per part. And this is processing that 2 by 2 by 1 centimeter part. Just to give you an idea, this model that we put together, what we did is we went out to actual producers. We collected data on actual equipment for both the vacuum and the continuous. So what you're seeing here is a model that we've put together based on real data. And we've been accurate enough that we're able to predict our cost per load within about $50 of a vacuum furnace, and likewise for a continuous furnace. So the model is being used for folks in pricing, and it seems to be very accurate. And I'll mention to you some of the assumptions that we've made in terms of cost, and we've tried to be very conservative and running on the high side of the cost so that you can trust the values. And so if we look at the breakdown of the cost of this continuous furnace, you see that, the vast majority of the cost is coming from the atmosphere, because this type of a furnace would run 100% hydrogen, or potentially a hydrogen, nitrogen, hydrogen, argon mix, depending on the product that you're running and what you would like to do. The next thing is the cost. So you see cost and atmosphere are your biggest, and then third would be the actual utilities at 15%. If we then, so let's talk about that atmosphere, that big chunk, that it's going to be hydrogen. You need to have medical grade quality, 99.999% pure, just like any hydrogen-based sintering process. And this can be delivered as gas or as liquid. Most folks are going to be using cryogenic, and that means that it would be delivered as a liquid. You'd have a long-term contract. You'd have a tank. And for this comparison, we use $2 per 100. Now, this is a little conservative. The prices that I was given here recently was right around $1.50 per 100. But so that we were safe and on the conservative side, we've used the value of $2 per 100 standard cubic feet of gas for the calculations. And we use this for both the vacuum calculations as well as the continuous furnace calculations. Keep in mind, those who would buy a 4.5 cubic foot vacuum, although you'd be flowing lower volumes, which is very true of gas, you probably wouldn't put in a cryogenic tank for that. You'd use a tube trailer, or you'd use just cylinders. But that cost is going to take you to a value of somewhere between $4 to $6 per 100. Now,
Steve,
for this, yes. Mm-hmm.
Sorry, we have a question that's a couple of slides back, and then we also have a poll that we wanted to talk about the cost of where the general cost to center a part is today for our attendees. So I'm going to run the poll, and then I will ask you the question while we're running that poll.
Okay, so if I understand correctly, what we're asking is, what do you consider to be what you expect your cost per part to be to debind and sinter?
And then Joe Lang had the question, approximately how many boats per hour would be exiting a full furnace?
Honestly, I'd have to go back and actually look at the calculation. I did it based on parts, and what I did is we looked at if we had a 6x8. Basically, what we were doing is we were allowing about a centimeter spacing between them. So just say that each part was about 3x3 spacing. So let me just get my calculator out here very quickly. apologize, I have to turn this on. Should be able to. And what I can do is, Joe, if you want to just send me, email me the question directly, I can then actually do the actual number of boats for you. But I don't have it offhand right now. But let's see here. So I'm figuring 25 parts per boat, and I'm looking at 50 weeks per year minus the maintenance time is how I calculated it. Okay. And do we have an answer on our poll, Sharon?
It looks like most people are running a 50 cent or less cost per part for sintering.
Okay. All right. Yeah. And so what we can do is let's go back and we'll talk. Let's look at how our cost breaks down for a continuous versus that vacuum furnace. So that 4.5 cubic vacuum furnace, you see that 42% of the cost is utilities as compared to 15%. However, 43% is due to depreciation. So when you look at it, the actual utilities and atmosphere costs end up being very comparable to just the straight utilities cost of the vacuum. So they're very comparable. It's just what you're doing is you're robbing Peter to pay Paul, right? Whether you're paying this in your utilities because you are water cooled on a vacuum, and so you're constantly pulling heat out, so you're less efficient in your energy. We're using the cost to purchase atmosphere. It's 6 of one, half dozen the other. Okay, and like I had mentioned, one of the other things about the continuous furnace is that we do use this lower cost design, 4 zones of debind in the front, 3 zones of high heat control. But what's nice here is you get a lot more flexibility with this type of furnace. I get asked a lot, well, how quick can I change over? Well, the truth is you can change over very much more easily with this type of a system than a continuous. For a continuous, if I load 316 into my continuous, into my batch furnace, I have to heat it up, run my cycle, cool it back down, unload it, then I can change over to the next product. Okay. Now, depending on the cycle time and how you run it, that could be anywhere between 9 hours to 22 hours, right? In the case of a continuous furnace, all we need is to wait. If we want to change the high temperature zone, change that setup, all we do is wait till the parts exit into that neck on the right-hand side of the hot box. And at that point, we can start changing the temperatures because our last boat would be in the cooling section. We could already have loaded parts into our debind. We could be going through our debind, and our temperature can be changed at 50 degrees C per hour. Okay. And you're going to push a plate about every, 20 to 45 minutes, depending on your cycle. So that being said, because you've got roughly a 120-inch preheat and 115-inch high heat, that gives you about plenty of time to actually start loading your new product in while changing, and you're only going to lose roughly, you figure about 15 boats of product, and then it'll continue on. So you can actually change while you're processing. So it's actually very flexible. you would not be able to change that quickly in the case of a batch furnace. The other reason that you want to consider looking at a continuous system is uniformity. In a batch system, it doesn't matter what type of a batch system you have, you're always heating from the outside to the center, right? So the part that's in the center of the load is not going to see the same thermal history nor the same atmosphere flow as the parts on the edges, especially those parts that are in corners. I've heard many people talk about having difficulty even running parts in the corners of a load and getting uniform properties and performance compared to the center. And, we've actually seen measurements that are with a delta T as high as 17 degrees C from corner to center on a batch system. Likewise, in a continuous, when we instrument this and we measure it, we're seeing about as little as a 3 degree C variation. Typically, it's somewhere under about 5 degrees C variation around through the boat. The reason is every part in that boat sees the same thermal cycle. Each one is exposed to the heating elements the same as the part next to it. So the thermal history of that part is very uniform. And the advantage to this thermal uniformity is when you have better uniformity, you have better quality because you have better consistency. Your variability goes down. That translates into a better quality product being delivered to the customer. Now let's talk about maintenance, and this is a big issue with a vacuum furnace. If we look at a vacuum furnace, we have to look at the condensation of the binder, right? Because you have that cold wall on the inside of the chamber. You can see here in the very first picture, in the center, how that binder can condense, and so that cold wall, you have to wipe it down every run, and that's going to take you about 15 minutes. And then if you have to clean the trap every 2 weeks, as you can see in the center picture, and that takes about 2 hours. The pump also needs to be cleaned quarterly. That's about 4 hours. And then it's recommended by the manufacturer that you do a burnout every month, and that takes at least a day if you're running a 22-hour cycle, right? So then if we look at actual replacement of like the hot zone and the retort, if we say we're going to replace that on average every 5 years. I mean, some people see 7 years, some people see 3 years. So let's just say it's 5 years. That's going to take about 2 days, and it costs about $200,000 to replace the hot zone. Going to have to replace the moly trays annually. We put about $10,000 in there. We've replaced some ceramic trays annually, about $10,000, and then miscellaneous annual, maintenance, thermocouples, valves, that kind of thing, because you do have to replace some of the valves now because of the binder. It's about $10,000. So altogether, over the course of the 5-year period, we're looking at about 12 weeks of downtime and about $350,000 in cost, okay, over that 5-year period. And please note, those numbers were given to us from actual producers and users. We didn't make those up. Then we went out and we looked at actual users of this technology in a continuous and tried to sum up all of the maintenance cost as well there. In this case, you'd replace the stainless steel muffle every 5 years, because remember, now we're going to use that stainless steel muffle as in that debind area, okay? And so it's a lower temperature. We're going to be somewhere between 500 to 650 degrees C. So the muffles last a long time. 5 years is actually pretty conservative, to be honest, in that temperature range. But let's just say we're going to replace it anyway. It's going to take about 5 days, and the muffle's going to cost you about $12,000. You're going to replace some elements every 5 years. Okay, it's going to take roughly 8 days, and we're taking into account the fact that insulation is going to take time to cool down so you can get into it. So it's going to be about $5,000 to replace the elements. You're going to replace some of the pusher boats, about $5,000. They're Molly boats. And then some miscellaneous maintenance items, we put about $2,000 in there. That's what they see. So over 5 years, your maintenance is going to be somewhere around that 2 weeks every 5 years and about $52,000 as compared to 12 weeks, $350,000. Okay. And so these are the values. We put these into our model. Okay. And so when we compare the 4.5 cubic foot vacuum furnace, and this includes the maintenance costs, the atmosphere costs, the capital cost amortized over 15 years. The only thing it doesn't include, which actually is conservative for, and it would actually raise the cost of the vacuum, is we didn't put the actual operator cost in there, and because of having to load and unload and do the different maintenance. Okay. But if we look at this comparison, the blue line is the cost of the continuous furnace, and the yellow line is the cost of the vacuum. And you see that we cross right about, between just a little over, right around 450,000 parts, 475,000 parts. And so what this is saying is when you're using about 50% of your capacity on the vacuum furnace or the continuous furnace, it's actually becomes cheaper to run the continuous furnace. Okay. Plus you're getting that better quality component. Now, the other thing to notice is on the far right of the graph, you notice that there's a jump in the yellow line or the vacuum line. That's because once you hit 800,000 parts, you would actually have to buy a second vacuum furnace to produce above that volume, where the continuous furnace does have a slight advantage. You can produce, like I say, slightly less than 1.1 million parts per year. The other thing to consider is the types of materials you want to process. Now, everything we've been talking about to this point has been high temperature, right? Things that are centered, centered in above 1150 degrees C, such as the 316, 17.4, that kind of thing. The other types of materials that are being produced in additive, and it's growing, is copper, and the big one in development and with the most potential is aluminum, right? And those materials actually are processed below 1150. And there's a reason that I point this out, okay? When you look at the high temperature sintering furnace, okay, the high temperature sintering furnace, easily goes to 1430, 2600 degrees to process your materials. We can do, like I say, about a little over 1 million parts on a 6x8. If you need to go higher in volume, naturally you could go to a 12x12 pusher plate, and that would be in excess of 3.5 million parts a year. It is a low-cost construction with fiber insulation in the debind, and wire wound in the debind, and brick and moly in the high heat. Okay. However, the low temperature, this is a different design, and it's because in this temperature range, to be able to control your heating rate, and as you know, aluminum has a much lower melting temperature, right? So you're going to be well below 700 degrees C. In this case, you lose your radiation from the elements, right? The elements are running at a lower temperature, and to be able to control this heating and to be effective, you need to have convective heating. And so this type of a system actually has a convective heating component to be able to control the heat up and control the temperature uniformity, to be able to debind and sinter these lower temperature and materials that have a much smaller window to where they melt and versus where they sinter. So this type of system is a different design, uh, the lower sintering temperature materials. And so,
And
as I said, yes.
I was going to say, while you were talking, I posted our poll about how many are producing or planning to produce low temperature materials like copper and aluminum. And
Okay.
everyone who's answered so far is planning on producing with those materials.
See, and that's really important then, because in the case of the of a vacuum, you don't have the advantage of that convective heating. It's truly a radiating heating package, and so to process that in get the control, we already see the variability even at the high temperatures. At these lower temperatures, your variability goes up much more. And so that's why it's so important for you to have convective heating. You have in this case, we would have a stainless steel muffle that goes down through. It's all wire wound elements. Or it could be silicon carbide, whichever you choose. We could split that as well, depending on the design and the process that's desired. But it would be a lower cost option and as compared to the high temperature. And in this case, we would then run a wire mesh belt. It would not be push trays. The parts would be run right on the belt, and it'd be using a nitrogen and hydrogen atmosphere, depending on the temperatures and what you would be doing. In the case of the low temperature stuff, it would be in primarily nitrogen, such as aluminum. But if you were running the copper, then you would use a hydrogen nitrogen blend. Okay. So really, in summary, I mean, high volume production is here. I mean, people are moving into that area. I know of a number of facilities that are producing well in excess of the 475,000 parts a year. Continuous does not mean too large. You can see that it's in direct comparison, and actually, in many cases, it's a lower cost option to a batch system. So continuous means that you can get lower cost per part. You can get better quality because of that uniformity. You get a lot better flexibility because you can be changing over while parts are still being processed. It is a lower maintenance technology, and can optimize this for the materials that you choose to process. And I'd really like to say thank you to Freeform Technologies. They really helped us out a lot to test our model and be able to see, validate one versus the other. And I'd like to remind you that if you don't already follow us, please scan the QR code. That puts you in for the drawing today, and also helps us to let you know the things, our new developments and new activities and things. Okay. And I thank you very much. Also, I mean, other things that we have coming up in May, we have a continuous furnace and brazing symposium coming up in Charleston, May 10th through the 12th. We're going to have an additive manufacturing webinar in August. Another one related to things. We've been doing a lot of research in the area of additive. We just presented a paper at AMUG showing that we could reduce the debind cycle by as much as 68%. We did that work with Oak Ridge National Labs, University of Tennessee, and Penn State, as well as Freeform. And so that's a huge step forward for our industry, showing that you can reduce that cycle time. And we showed what the optimal debind time is. It's not a MIM cycle. And we actually did the TGAs and things. And we're going to continue that research, and that'll be presented at AMPM and PowderMet, as well as we'll be at Rapid. We're going to, at PowderMet, we're also going to be talking about some alternative printing technologies that allow us, where we've printed FCO208 conventional 150 micron powders and sintered them. And we're going to talk about some of our work in that area, as well as some other things as related to like ballistic ejection and how to deal with it once you know, because oftentimes you don't know if you have ballistic ejection. So once you process the part, is there a way that you sinter that can help to mitigate those issues that are caused by ballistic ejection? So we're going to talk about those things at PowderMet as well. And then we'll also be at the battery show in September 12th through the 14th. So please look us up, and like to invite you all to attend the different papers and webinars and things. All right. Well, thank you very much. That's our webinar for today. And if you have any questions, we're open to some questions. Do we see anyone with questions coming in now?
No more questions at this point.
Okay. And Joe, please send me an email. I'll tell you exactly how many boats per hour that we did on the model. I'll just open it up and tell you exactly what we did there for the calculation. And then if you have any other questions, we can run the model or talk about it or go through things at that time. And please, I open that up to everyone. Anything that we can do, if we like to have further discussions offline, we're available. Please reach out to me. It's sfeldbauer@abbottfurnace.com. And why don't I just put there's my information. Please reach out to me, and I'd be happy to answer your questions offline as well. Okay.
All right. Well, thank you everybody for attending, and we look forward to seeing you at our next webinar, which will be in August. So follow us on LinkedIn, and you'll see a posting of the next webinar.
All right. Thanks, everybody. Have a great day.
Bye-bye.